In this video, we're going to learn how to take the determinant of an upper triangular matrix or a lower triangular matrix. Turns out it's going to be a really nice and easy algorithm. So we're going to talk about linear algebra, matrices, determinants, today on High Peak Education. What's going on, everybody? Here we have a video that is sort of high level in terms of linear algebra and matrix multiplication in terms of determinants. So what we're going to do is we're going to develop the formula for an upper triangular matrix or a lower triangular matrix. It turns out it's going to be the product of all the values that are along the main diagonal, and we're going to get into that right now. So here we have a numerical analysis and actually a linear algebra problem that I'd like to work on. So let's have a look. It says, let A be an n by n upper or lower triangular matrix. Prove that the determinant of A is equal to the product of its diagonal entries. In other words, the determinant of matrix A is equal to A11 times A22 all the way up to times ANN. Okay, so first of all, let's start off with the easiest case we could think of. What would a 1 by 1 matrix look like? Well, it would be 1 by 1. So it would just be a single entry, n equals 1. And notice it'd only be A11. And the determinant of that is just literally A11. By the way, we do row, column. Now, by the way, most places do 1, 1 like this, but it's really 1, 1 and 2, 2. I mean, it's row, comma, column, but many teachers and many people omit sort of the comma here, separating row and column. But just know that the first subscript is row, the second subscript is column. What about a 2 by 2 matrix? Let's assume the 2 by 2 matrix is going to be upper triangular. So I want to do this proof for upper triangular matrices, but the determinant argument for lower triangular is very similar. So we can prove by induction for an n by n matrix, but we'll start with the 2 by 2 matrix. If matrix A is upper triangular, notice that upper triangular means there's only data along the main diagonal and above the main diagonal. There are only zeros below the main diagonal. So notice that there's 0 here, everything else is filled in with something that is not 0. In fact, A11 and A22 need to be non-zero. In fact, I mean, they could be 0, but then this entire determinant is 0. 0 times anything. If there's any 0 on the main diagonal, the entire determinant is 0. It turns out that we know the determinant of a 2 by 2 matrix is we take these two multiplied by each other times these two multiplied, or sorry, subtract these two multiplied by each other. That is A11 times A22 minus A21 times A12. Well, A21 is equal to 0. So we just get A11 times A22. So notice that the product of the diagonals for a 2 by 2 matrix is indeed the determinant. What about the 3 by 3 case? Well, the 3 by 3 case would be the following. Notice that here's a 3 by 3 determinant. Okay, so this is 3 by 3. So hopefully you're aware of how to calculate the determinant of a 3 by 3 matrix. So this one is 3 by 3, and what we have here is the formula for calculating the determinant of a 3 by 3 matrix. Notice this formula is generated by what's called cofactor expansion. What is that? Well, cofactor expansion is basically we're producing several 2 by 2 determinants. So that is this one, and then this one, and then this other one, where they're basically the lower parts of the 2 by 2 determinants of the entire 3 by 3, except that we start in the upper left-hand corner, and then notice that what's in the upper left-hand corner actually goes down here. That's A11, and then you cross out the column and the row associated with it. Now, by the way, there's a positive that goes out in front of here, because it turns out that whatever the subscripts on the cofactor are, that is on the A11, you put those as the exponents. So it's -1 to the 1 plus 1 powers, which is really just a -1 squared, which is positive. So this is positive. but then we're using this 2x2 determinant, which is A22, A33 minus A23, A32. And then what we do is the next cofactor is A12, but then there's a minus here because it's -1 to the 1 plus 2 power, which is -1 to the third power, which is a -1. Now, by the way, -1 to any even power is just +1, that's +1, and -1 to any odd power is just going to be -1. So notice the next one here will be a positive. And then with the second cofactor, you cross out the top row and cross out the middle column. And then we proceed to the third one as well. Now, by the way, notice that produces this formula, but remember, we're doing this for an upper triangular matrix. So assume that there's only data here and that there are zeros here below the main diagonal. Well, if that's the case, notice that what we're going to have is we're going to have many of these terms being 0. What do I mean by that? Well, notice that we're only going to get data here, A22 times A33, and then times A11 out front. But then this part right here is going to be 0, because this is 0 right here. This is 0, this is 0, and then these are all 0, so then each of these determinants will be 0. So notice that only this front expansion using the cofactors is actually non-zero. Now, with all that being said, notice that we're just going to get +1 times A11, A22, A33. So notice this formula seems to work if you have a 3x3 matrix. So basically, one of the ways we prove in mathematics is what's called the inductive hypothesis, or using inductive reasoning. We prove up to a certain point, we assume it's true for n, and then we prove for n plus 1, and showing that n plus 1 is really the same thing as case n, just with an extra 1. So now let's follow the inductive hypothesis. So expand the determinant with cofactors from the first column and use the inductive hypothesis. So let's have a look at this. Notice that if we expand this, what are we going to have? Well, we're just going to have each of these things, so it's just going to be -1 to the, and then what's the next determinant going to be here? Well, notice that if we've got -1 to the 1 plus 1 power A11, then we're going to have -1 to the 1 plus 1 times A11, but then we're going to have -1 to the 1 plus 2 times A22. Or sorry, it's actually going to be -1 to the 2 plus 2, because again, this is the cofactor, A22. And then we're just going to keep on going down, because as soon as we get this one, and the rest here is the only part that stands up, we're just going to keep going down the diagonal. I hope you understand that, because the only one that stood up in this 3x3 was the A11. The next one that'll stand up is the A22. The next one that'll stand up is the -1 to the 3 plus 3, A33, and so on and so forth, all the way down to ANN. So if you think about it, all of these are equal to +1. So all of these -1s to even powers. And then notice that all we're left with is A11, A22, A33. So that's exactly what the determinant is. That's what we set out to prove. So note that the remaining terms in the expansion are all 0. So what we find is, using the inductive hypothesis, we know that the determinant of an n by n matrix is just the product of the values along the main diagonal, namely A11, A22, all the way down to ANN. So this is the answer required, and the proof is complete. Now, by the way, one more thing. You may ask, well, that's all well and good for an upper triangular matrix. What about a lower triangular matrix? Now, by the way, do you see that we proceeded from the upper left to the lower right on a upper triangular matrix. For a lower triangular matrix, notice that all you would need to do is you would need to do cofactors, but you would need to start in the lower right corner because all the terms above the main diagonal would be 0. So the proof is almost exactly the same. So that's what I've got here in this pink color. But notice that in a lower triangular matrix, you start with the last column. So instead of starting in the upper left with the first column and then do cofactors down in a cascading way, you start with the lower right and then just cascade up. But you're still going to get A11 times A22 all the way times ANN. But the first one you'll find is ANN. The next one you'll find is A subscript n minus 1 comma n minus 1 for row and column, and then you just keep going. So the proof is very, very, very similar. So I'm not going to go through that proof, but hopefully it stands to reason that this is indeed the case. Okay, I hope that makes sense for this. So what we saw here is that any upper triangular matrix or lower triangular matrix can collapse down to a very simple formula, namely just the product of the entries that are along the main diagonal. Of course, we have to have a square matrix, it has to be invertible, has to have non-zero determinant, all this kind of thing, but otherwise we can calculate the determinant using this method. We just used cofactor expansion and then just cascaded on down from the upper left to the lower right if it's an upper triangular matrix, or we went from the lower right to the upper left if it's an upper triangular matrix. So I hope this was helpful with your linear algebra, with your matrix calculations, and let us know in the comments if you want to see more videos similar to this on this channel. Thank you for watching High Peak Education. Please smash that like button if you enjoyed this content. Please subscribe to the channel to grow the channel. Social media links are in the description down below. Please support us and thank you for your attention. We will see you in the next video.